This week, folks, we will be doing an aldol condensation. So what is an aldol condensation? It's the chemical combination of two compounds that contain carbonyls. Oftentimes the product has an aldehyde and an alcohol. That's how you get aldol, but it can also be done with ketones. Important for this type of reaction is understanding that these carbonyl compounds can have keto or enol forms. So either the carbonyl or the alkene with the alcohol. But why is this reaction important? So it's a useful way to form new carbon-carbon bonds. Organic chemists love coming up with new ways to do this. But it's actually used in, pharma in labs today. Particularly, it can be used to synthesize ibuprofen. So if you've taken Advil, you may have taken something that was made with an aldol condensation. And the product and the functional group found there is often called an olefin. So if you've seen that word, think aldol. Now let's talk about the reaction itself a little bit. So when we're doing aldol condensations, the first step is always to form a better nucleophile. Generally, we call those enolates. And so in order to form this kind of enolate, we need to look for first the alpha carbon, and then if there is a proton available at that alpha carbon. So looking at the reactant on the left, there is no proton to abstract at this alpha carbon. Alpha carbons are those that are just next to the carbonyl carbon. If you take biochem in the future, we'll also use this language of biochem. Additionally, in this aldehyde, the proton coming off the aldehyde is not alpha. So there's nothing that we can really do to abstract here. However, in our other reactant, we do have alpha hydrogens. So this reaction is quite specific, since we'll only be forming one nucleophile and only be able to form one product. Now, once we abstract a proton there, we'll have a good nucleophile. We'll have to keep in mind, though, that those protons are not very acidic. This is why we have to use the base catalyst, and this is why we have to wait for about 15 minutes for that nucleophile to form. Once it's formed, we can have nucleophilic attack on my favorite electrophile, the carbonyl carbon. And then we'll have done our aldol condensation. But you'll notice that in this reaction, we won't be done quite yet. We'll also have loss of water across a bond. So let's do the mechanism. Let's start by drawing our reactant where we will abstract that proton. There are our alpha hydrogens. Let's bring in our catalyst. So here's our hydroxide. Now, I'll remind us that these hydrogens are not very acidic, but over time we can abstract them. So let's grab one of those protons. And now we should be able to see why it's even possible for us to take one of these protons that, frankly, is pretty basic. It's because this is resonance stabilized. The enolate is resonance stabilized. So we know acids have stable conjugate bases. The reason we can take this proton is because the conjugate base is resonance stabilized. You might also notice at this point that we have kind of two possible nucleophiles. The first one down here, the second one up there. We have a negatively charged carbon and a negatively charged oxygen going on here. Although we have both, there's really only one good nucleophile, the carbon. Carbon is much more basic than that oxygen, and generally basicity correlates with nucleophilicity. So at this point, we can do a nucleophilic attack. On our second reactant here. And let's draw what we get next. Oof, a lot of drawing. Okay, at this point we have our nice tetrahedral intermediate. And in the aldol reaction, the last step is generally a workup so that we can protonate and make that alcohol functional group. We do have a workup today, so we'll add some acidic water, basically hydronium, and that'll help us out in the process. So time for the workup, let's add some hydronium. At this point, we can protonate, making that beautiful alcohol, and really completing the aldol condensation. Okay, so technically we've completed the aldol condensation. However, there is one more step that happens in our reaction. When you see you have this alcohol formed next to conjugated systems, we will always lose water across the bond so that the conjugated system is extended. You see that we have sp2 hybridized carbons here, this carbonyl carbon, and then again on the right side. So if we can lose water across this bond and make these carbons sp2 hybridized, we will have completed the conjugation across the entire molecule. This is extremely stable, extremely favorable, so it always happens if it's possible. So folks, because loss of water will be incredibly favorable, we lose water across this bond. Thus forming our final product. And you can see now that we've lost water across this bond, the conjugation is extended throughout the entire molecule. That is extremely stable, extremely favorable. So that's why we do that little additional step at the end of the aldol condensation. That's the mechanism. Some notes about the protocol this week. The reaction will again happen at room temperature. So we're just adding a little bit of catalyst, and this reaction is able to move forward. We will be doing a workup in acidic water. So we're working with both sodium hydroxide and HCl. We have to be careful that we're having really good safety protocols so that we don't get any of this on our skin. We'll be doing another vacuum filtration. This week, folks, please do not use the vacuum pumps, try to use a water pump for the vacuum filtration. The vacuum pumps are going to be much too powerful. Those are really only good for really large filtrations, and if you do use a vacuum pump, you'll likely lose some of your product along the way. It's just a little bit too powerful. Do always wash with cold solvent. Cold solvent is great. It'll wash away impurities, but at the same time, it will not dissolve your product. We don't want to lose any of our product. So make a little ice bath and get some solvent chilled. Finally, we'll be doing a recrystallization after filtration. You want to get some solvent prepared and warmed up on a hot plate. Cover that solvent with a watch glass so it doesn't just evaporate away. And if it's already hot, your recrystallization will run much more swiftly. Finally, folks, two different things to mention for green chemistry as we work our way through all the principles of green chem. Safer solvents and auxiliaries. Think about the solvents we use in lab this week. Are the solvents generally safe? Are they toxic? Could they be made more safe? Think about what we use to do the reaction in. Think about what we use to wash crystals. All of those count as solvent. Additionally, designing for energy efficiency. So doing these things at ambient temperature and pressure. Super important. We want to make sure that we don't need to add additional energy into the equation, because that is technically more wasteful than doing it at room temp. Comment about these things in your conclusion. I'll leave you all with this week's cat meme that is related to Aldols and alcohols. See you in lab.